All jokes aside, my name is Ted Tiffany. I'm our Director of Sustainability for Gutman and Blabowit. We are consulting engineers. We are electrical, plumbing, HVAC, telecom, commissioning, and I run our building performance team, which is really a lot of codes and standards work, compliance with Title 24, LEED certification, those kind of things. That's my day job. I probably have about 2 or 3 other volunteer jobs that are like my other 40 and 60 hours of the week. Right now I'm working that went backwards. I'm working alongside the Building Carbonization Coalition. I'm an advisory board member. I'm also on the LEED Technical Advisory Committee, so I get this lens of decarbonization in many facets, not just for California, but for the LEED standards nationally and globally, how we apply electrification policy, decarbonization, and even grid harmonization. We're developing those credits for LEED. So I do a lot of work in California, but I do a lot of work internationally as well. So right now, my colleagues are at the Carbon Positive conference down in LA, and they're rolling out the primer document for the decarbonization of the built environment, design professional guide. So we're writing right now kind of a technical guide for owners, developers, contractors, engineers on what decarbonization means in terms of electrification, but also grid harmonization. And we're getting a couple of chapters in there for embodied carbon as well. This is funded by Google, Microsoft, Healthy Buildings, AIA California, WRNS, Urban Fabric, and a whole host of volunteers. And I know there's a few in this room, but we are looking for more volunteers to help us develop this guide. So come talk to me afterwards. We're still looking for funding as well. But Microsoft, for one, is going to use this guide to give their global developers, this is our strategy for electrification and decarbonization. They're fully invested in all electric buildings in the climates that it makes sense, and other strategies where it doesn't make sense right now. So if we're designing in Arkansas right now, an electrified building will actually increase carbon because of the carbon content of that grid. So something to be aware of. This guide will lay out some of those issues and lay out the technologies that I'm going to talk about today. I've also been working with local agencies, both with the agencies themselves and the developers that are bringing projects in, saying, I have to comply with your electrification policy. I don't know how to do that. This is costing me too much. Here's where my pain points are. Here are the things that I know to be true. And we're working with them to say, here's another strategy. Here's a cost impact that you may not have. Here's some technology that you can apply in this way. So I'm kind of going to work through a couple of these myths and strategies and some of the things that we've seen in our design firm, both for our projects, but for other architects and engineers that we've been consulting with, and some of the projects that have been brought in for developers. One of the things that we get challenged with a lot, and this comes in a challenge late in design. So we've got projects that are coming in past the DD set point into CDs. Some of these challenges are bigger than others. And we talked about the cost impacts. Later in design, cost increases for changes are much greater than in early design. I say anybody in an early design for electrified building is going to be cheaper, right? If we're in CDs and we have to retrofit, these issues start to come up. One is space, right? So we have a big building that's a 6 million BTU boiler. It's about the size of Draymond Green, right? We don't need much space for that. And I've had a couple people come in and say, well, we're going to electrify. We're just going to put this electric boiler, same size, same BTU output. But the energy code won't allow that, right? We don't allow straight electric resistance boilers on this scale. You can't get it through prescriptive. You can't get it through the performance approach. But I've had at least 3 projects come to me and say, this is our solution. Did you check with the energy standards? Do you know that this can't be done? So we're talking about heat pumps. And they come to me with this solution. Well, this is how many heat pumps I got to put in to electrify my building with heat pumps, where I'm never going to find space for this, right? Well, heat pumps are not boilers. they like to be paired with storage. And storage is a great thing. One, it gives you some grid harmonization capability. Two, it allows you to downsize the number of units that you need and draws down the electrical connections as well. So one of those cost savings is drawing down the number of units and the placement of units, and then we can talk about where the storage needs to go. I have to give a shout out to a lot of the folks that are colleagues and collaborators, sometimes competitors, but there's a lot of people doing a lot of great work, collaborating with colleagues, collaborating with the Energy Commission, trying to elevate the industry to really start thinking about heat pumps in terms of hot water heating differently. They're not boilers. So Sean Orem at Ecotope put this presentation together, and it was really stunning. And we've been working with them trying to look at different configurations of central heat pump water heating and even thermal loops. And designing design tools for the manufacturer. So we've been working with Nile and Colmac and Sandin and all of these other manufacturers to really kind of get design tools out to the community for our engineers to understand how the sizing is different, how the sizing of storage can equate to longer periods of downtime for those heat pumps, and right size those. So in most buildings, we may have a small mechanical room that we have limited space for storage. Then we need to relocate those on the roofs. These design tools that they're building and working with the Energy Commission to put the calculations in the design tools, in the compliance tools, really helps our industry. So I have to give a big shout out to folks like Redwood Energy, the Energy Commission. Danny is, the Energy Commission, usually planning on a 3-year cycle, has been so nimble in the last 6 months to a year and have worked so hard. So Danny, thank you, and send it back to your team on how hard you guys have worked, and the industry really appreciates it. So, but there's still a lot more development needs. We need more products to market. We've been myth-busting this, that heat pumps can't work in cold climates. So there are products on the market that can work in Lake Tahoe, in freezing and below, and produce hot water at extreme temperatures. They are the CO2-based refrigerants, which have a global warming potential of 1. This is where we need to move the market to, the CO2-based refrigerants. And then we can even do CO2 capture for those refrigerants. But not all the industry is there. We're still on some of those legacy refrigerants, but this move to the CO2-based refrigerants can actually help us work in cold climates. So this particular unit, this is the Maekawa unit, can produce, up to 194 degree water. So that's kind of high temperature loops that we can really start to put. We don't need 194 degrees. We're usually about 140, right? But some of those campus central loops are still on that legacy temperature. Keep getting this. There's no products I can find on the market. I didn't list all the products on the market. These are just the most common ones. And that Sandin unit right there is the mini split version. So tank, retrofit, option for homes right there. And that's the CO2 based one. The rest of these are on the legacy. This is a CO2 based. These are legacy refrigerants, but still good units. So these are really for small markets, retrofit projects, new construction, unitary products. Oops, sorry. Central systems, getting more and more on the market for central systems. Colmac, Nile. We've got a Maekawa unit running on a winery that I'll show you in a little bit, and more coming to market. I think before Kovo hits, I was planning a trip to Japan to start to talk about the manufacturers over there that need to come to market and what they need to break down barriers for this market. But we're having phone conversations. These keep getting larger and larger. So these up to 1,000 MBH, and these can be paired with Colmac applications. So you can run them in series up to huge hot water loads for, like, say, healthcare. Large and central heating and cooling plants. We can stage these up to almost 1,300 tons with the multi-stack. And these are more for big central plants, for big, tall buildings that are both hydronic loops, chilled water loops, hot water loops. Right? And then these can be paired to do domestic as well. So the scale of projects that we can do, I keep getting questions about, can we do high rises electrified? Yes, we can. We have the technology to do that. Can we do hospitals? in this fall, I was at CleanMed, and we gave a talk for an hour long about the technologies we need to decarbonize healthcare. And I had a bunch of the developers come up to us and say, yeah, we can do it. If Stanford can change their entire central plant servicing the entire campus, they're running 96% electrified at this point. They have a small boiler that kicks on in extreme temperatures that they're still trying to design out. But if you can electrify a campus of that scale, we can do it on individual buildings and even a high-rise. So I get this question a lot. What are my electric service impacts? I had a developer bring me this to the table, and they said, I am going to have to put in 0.5 megawatt electric resistance boiler, and I need to bring in an additional service from PG&E to service that load. There's no way I can afford to do this. This is ridiculous. I said, well, first off, this is an electric boiler. You can't get that to work under the energy code. What we're talking about is a heat pump strategy with storage. Says, oh, okay. So we go out to the manufacturers. That load drops to 144 kW. And this is a really large apartment building. This is over 100 units, so significant. And that stayed within their service size and dropped down the electrical connections, dropped down the cost of the systems. So one strategy. One of the things I keep seeing, and some of this is based on the REACH code, but some of it is interpretation from the REACH code about electric service for EV charging. So we have a project now that has every parking spot serviced with an electric charging station, and that's a significant load. And if these REACH codes are requiring future connections, not just conduit, but electric capacity for that, that's going to be the bigger impact than the electrification of the building systems. As we're bringing all that load for every parking space, or 50% of the parking spaces, that is a significant load for vehicles, and that is impacting projects. We've got to have some strategies around load limiting car charging stations, load sharing capabilities, and on that particular project that I just showed, we're trying to see if we can share load with the domestic water systems with the EV charging stations, because those are kind of paired loads, right? We want everybody comes home, we get through that tank draw for the central heat pump water heating system, and then after that is recharged, then we can start charging the car charging stations, right? That technology needs to be enabled. I've seen a couple of retrofit products that can do that. They can share single car charging stations with single dryer outlets. That technology is to market, but in new construction, we still have some code barriers. So that's the discussion there. This is our Sonoma Clean Power headquarters, and this is every parking space has a charging station. And this is one of the drivers of our electric service upgrades there. So keep that in mind. Retrofit opportunities, right? This is a fairly simple office building, right? 15,000 square foot building, gut renovation, decreased load by insulation, applied rooftop heat pumps that are fairly simplistic. The zonal controls are a little bit more advanced. But this one has the enhancements of all of the car charging stations, stationary battery storage, PV systems. But other than that, it's a conventional electrified retrofit of a 15,000 square foot building. Fairly simple, except for all these grid integration elements that they want to play with. And Sonoma Clean Power is using this as a learning opportunity for other retrofit projects. But the building retrofit, taking gas out of that building and applying off-the-shelf technology, was very straightforward and very cost-effective. Okay. SMUD, East Operations Unit. No gas brought to this campus. Obviously, they're an electric utility. But again, straightforward architectural design, very tight envelope, get those loads down, and then serviced by a central heat pump plant. So all hydronic systems. Silver Oak Winery. This is up in Geyserville, Healdsburg, almost Geyserville, in between. All electric. And this is a very heavy load-driven industrial processing plant. You ever seen a winery processing plant? it is like an oil refinery, only they're making better stuff. But this was a living building challenge building, so they weren't allowed to put gas on this project. They're only allowed a small backup for propane because they were worried that they weren't going to have any, they needed additional load for the industrial process wash down facilities. So they do a lot of tank washing, barrel washing, winery waste, and they actually have what's called this MBR system. So they have the wastewater treatment, black water treatment system on the site. This is an incredible load, almost 16% of the entire winery process. This is a project that Christine Condon put together and was incredibly accurate about predicting all of these energy use processes because the developer had to, for every kilowatt hour used, they had to provide on-site power for it. So it's a very accurate calculation. We've been commissioning this project for them, but very accurate prediction. And this is ammonia-based chillers, huge cooling needs for tanks, but you can see the admin tasting kitchen, all electric, complete tasting kitchen, all electric. And then all of these loads that are traditional for the office building are very small compared to the industrial process. But a Mayakawa heat pump water heater working very well. They have not had to refill the propane tank on this building at all in the last 2 years of operation. So just another look at it. We're doing a huge decarbonization effort at Santa Rosa Junior College. And if you're not aware of what's going on at SRJC, you need to really start to study it. One of my former students is now their director of sustainability, and they are strategically retrofitting buildings to connect to the geothermal fields that we just put in. Taking buildings off of gas, putting them over to air-to-water source, and sometimes air-to-air water heaters, but strategically connecting buildings to the new geothermal field. The challenge, I think, with geothermal in this climate is we don't have a lot of drillers. They're all in Colorado, Idaho, Wyoming, because geothermal is common up there. My mom's house in Idaho was built 30 years ago, had a single geothermal well loop and a geothermal heat pump in her system, 30 years old. And that's common in those cold climates. We designed Curry Village in Yosemite Valley. They didn't want to bring propane trucks up. Geothermal well, 100-year bore wells underneath the parking lot there, all geothermal heat pumps, completely electrified in the valley. So we don't have those impacts of propane. But they got a $5 million CEC grant to do microgrid applications on SRJC. So they've got the PV systems up and running, they got their battery storage in place, and they're starting to do this carbon accounting and microgrid applications so that they can go into islanding mode when we get power shut off. A lot of exciting things happen over in my backyard. But this is just a look at the geothermal wells going under the parking lot, going under the Bailey Field where they play football, and their track. So they just did a huge track retrofit. So we coordinated all this to put in those bores before they put everything else back down. So this was connecting 5 different buildings and large-scale buildings. But just actually opening tomorrow, Friday, the theater will be open, and it's completely all electric. And this is actually one that we retrofitted to be all electric at 50% CDs, which is a little bit challenging. But they said, hey, take the gas off this building, take the boilers off. We want to connect it to the geothermal field that was in existing. And they said, we want to also expand the geothermal plant. So great story. Albany High School, K through 12 buildings, our learning centers should be the first to be electrified because everybody will learn from those electrified applications at the school, take it back to their homes. But these are fairly simple single zone VAV heat pumps and heat pump water heaters and 80 kW of PV to get them to ZNE. Not a challenge. Schools, not a challenge. Big housing projects. So this is an example of where we've used electric radiant heat. And this has been frowned upon in the standards for quite a bit. This project is a challenge. It's UC, has to be decarbonized, has to be all electric. It's also on UC Berkeley's campus. So their campus policy says you can't put cooling in the spaces. we don't need cooling, you can, suffer a little bit. But there's still a place for electric resistance, I think. But it comes with doing all the right things. So this building is almost a passive house standard except for the triple glazed windows. But really low U-factor windows, low SHGC glass, almost an R25 wall system, really bringing those architectural loads down. There's only about 2.8 kW in a 3-bedroom apartment, and pairing it with energy recovery ventilators. So any of the air exchanges being done with heat recovery, and then a small individual heat pump water heater per unit. So this simplifies a couple of things, especially for low-income projects. Metering, right? 1 electric meter per unit. Who's aware of the water metering requirements that were put in place on January 1st? Only Danny. So there's a new watering metering requirement. So if you have a central heat pump water heating system, you have to meter the domestic cold water to the unit. You have to then meter the hot water supply and return so that you can measure the amount of hot domestic water that's being used in the apartment. So this simplifies the metering requirements for just a single domestic water meter. It's not applied to low-income housing, so look at the exceptions. But this is a strategy where we paired that individual water heater, tanked water heater, right next to the washer and dryer exhaust, so that if it gets too cold in that space, we can exhaust that cold air. But we've got free cooling in the summer, so we didn't technically put in active cooling, but we've got some supplemental cool that comes off the domestic hot water tank. So that's my ethical use of electric resistance heating. I am not a fan of electric resistance heating, but essentially if our other strategy was to put in a PTAC unit and pay for, both heating and cooling, we would actually have to lock out that capability of cooling on that system per UC policy. So this is my only example of using electric resistance. I'm not a fan of just using straight electric resistance. Heat pump efficiency is where we need to be. UCSF, we've just been commissioning the Nile heat pump water heating systems at UCSF, and this is going to be kind of the model for UC housing projects now for central systems with either Colmac, Nile, or the other central systems. But operating very well. Heating COP of 4.15 is measured. Measured, Danny? Measured for the system. So we've talked a lot about the operational efficiency with these recirculating loops and degradation of the overall rated COP of the units. So this is the one thing that CEC is really concerned about. Rated efficiency on the units, the label that comes, is not the true efficiency of the entire system. So that's something CEC policy has been really looking at hard, and that's the investment that they need to make sure that we've got efficient systems coming on the market and are regulated that way. So I'm going to stop there and just take questions because I know I throw a lot of technology at you. But this is kind of what I'm seeing in the market and seeing coming through the lens of the local agencies, CEC policy and compliance issues. But this is going to be more common. So I wanted to introduce some of those technologies and some of those challenges, and probably covers a lot of the questions that you've had through local jurisdictions or for contractors and developers. So I'll take any questions you guys have.
We probably only have time for about 2 questions.
Okay.
So is it standard to put the electrical equipment in the basements now? Because flooding is often an issue. I mean, you think about Hurricane Sandy and
yeah. So and what's interesting in Sandy, when I was doing investigations on Sandy, the electric systems came back online within 14 hours, and the natural gas and steam systems were flooded and took almost 3 to 4 weeks to come back online. So there's resiliency components around the natural gas systems are interesting. But as far as locations, the tanks have some weight to them. Those we usually place in the basement. Rooftop units can go up on top. We have a couple of arrangements where the heat pump equipment is in the parking garage as well. So there's a couple of different arrangements. We've also looked at a couple of strategies to distribute storage on different floors so that we've got, we don't have, sometimes we have space issues, right? Putting the place tanks in one particular location in the building. So we're looking at distributing storage tanks throughout the building too. It also helps us with structural. Well, thanks you guys.